Hi everyone, this is the video lecture for the last day of multi-unit material balances that we talked about. And today's video lecture is going to consist of two parts. We're just going to look at two examples of the multi-unit systems and how we deal with material balances. One will be fairly straightforward, which will be the first one, and then the second one will be a little bit more complicated. So let's dig right into example one that we're going to look at first. Both of the examples we're going to look at are systems that have to do with reactions, so there will be chemical reactors somewhere inside of our system. Like I said, the first example is going to be one of the more straightforward ones. So we're going to have a reactor in the middle, followed by a separator, and we'll have some fresh feed to this reactor, obviously some product from the reactor to the separator, and then the separator will produce two streams. One will be our product stream, and the other will be a recycle stream that feeds around to our reactor again. So out here in stream 1, there's going to be 10 moles of A, and 10 moles of an inert that I'm just going to call I. Remember, inerts don't participate in our reactions, and so that's all that's going to be fed to our system. This will be stream 2, which is the reactor feed. Inside the reactor is the reaction A goes to B, and the single pass conversion inside this reactor is going to be 2%. Remember, single pass is dealing with just the reactor. We also saw an overall conversion, and we'll see that in a moment. The stream coming out is going to be stream 3, out of our reactor. So our reactor effluent coming out of our separator as product is stream 4, and as recycle is stream 5. So coming out of stream 4, as with stream 3, well, maybe not with stream 4. Stream 3, we would expect to see a little bit of everything, right? Some A, a little bit of B, and some inert. Coming out of stream 4 as part of the problem statement, this isn't an assumption you would have to make. I'm just saying this is part of the problem statement. We're going to get a little bit of everything, A, B, and I. But in our recycle stream, stream 5, we just have pure A. Right, so there's no B and no inert, and that's as a result of our separator. Our separator can do anything that we want. So here, as a process specification, we're seeing, actually not as a process specification, in the problem statement we were told that pure A is coming out. One additional process specification that we're going to have is that 10 moles of A are recycled for every 1 mole of A in the fresh feed. Right, so that's basically saying that our recycle stream 5 is about 10 times bigger in terms of A. It's got 10 times as much A in it as stream 1 does. So for every 10 moles of A coming around in stream 5, for every 1 mole of A coming in through stream 1, we've got the equivalent of 10 moles of A coming in through stream 5. And so our goal here is, can we determine the overall conversion of A, F overall, for a system like this? There are undoubtedly several ways to do this, so if you can come up with a different way other than what I'm about to show you, please feel free to give it a shot. We should end up with the same answer no matter which way we go. The first thing that I'm going to do is a degrees of freedom analysis. Depending on the size of the system, sometimes this is reasonable, sometimes it's not. If you only have a handful of units, then degrees of freedom is a good way to get started and to point you in the right direction. And we've only got about 4 units here, so it'll be a good one to get started with. As we'll see in the second example, sometimes you have so many places to start that we sometimes do degrees of freedom and we don't. So we'll see what that looks like in the next one. For this particular problem, the 4 degrees of freedom analyses that we're going to do are on first the separator here, the reactor here. So what I'm drawing are the control volumes we're going to use. There's another control volume here because we've got a mixer. And then the last control volume that we'll do is the overall system, which will be a system that looks like this. So these are 4 different units that we're going to look at. There's a reactor in the middle, a separator towards the right, a mixer towards the left, and then the overall system where you only have streams 1 and 4 going in. So let's take a look at what those degrees of freedom analyses look like. Let's look at the overall system first. So if I do a degrees of freedom analysis on the overall, we have to do a little bit of modification to the way that things are being supplied over here, to the way the information is being supplied. If we look back at stream 1, so our attention right now should be over here at stream 1, we can pretty easily figure out that if we know we have 10 moles of A, 10 moles of I, that we also have 20 moles total with 50% A and 50% I, right? So neither one of those would count as an unknown the way that we're given it. Over here in stream 4, so here now our attention is looking over here, all we know is that a little bit of everything is coming out. And so if we were to list what's unknown and known on a system like this, now we need everything, right? We need a moles in 4, and we also need YA, YB, and YC. Right, so let's put that over here in our overall balance. Our unknowns here would be the moles coming out in 4, the YA in 4, YB in 4, and the amount of inert in 4. And don't forget, we also get an extent of reaction because somewhere inside that control volume we have a reaction occurring. And remember, it's always the same extent of reaction, right? When we write this squiggle, it doesn't matter if that's happening inside the reactor and we're doing a control volume on the reactor itself, or if we're looking at the overall system. It's the same squiggle each time. The equations that we get, we still get our 3 material balances. So we'll get 1 on A, 1 on B, and 1 on the inert. We get 1 sum of mole fractions are equal to 1, and we will get that on stream 4. And that's all we've got. So the number of unknowns is 5, the number of equations that we have is 4, and therefore our degrees of freedom is +1. So if we look at the overall system, we're not going to be able to solve for all those variables. Let's take a look at another system. How about the reactor? So the number of unknowns that we have, if we flip back over to our drawing, and so here, now keep in mind we're looking at the reactor control volume here. We don't know anything about streams 3 here or stream 2 here. We have no knowledge about any of those. We do know a little bit about stream 2 if you were to look at what's feeding into stream 2. It has to be only A and I, right? The stream 5 is pure A and stream 1 is just A and I, so there can't be any B in stream 2. But other than that, we don't know anything. We do have a reaction, and then we do have this process specification as far as single pass conversion goes. So the reactor is probably not going to help us very much because the unknowns are stream 2 and 2. We don't know the amount of A in stream 2. We don't know the amount of inert in stream 2, nor anything about stream 3, nor anything about any of the components in stream 3. So YA 3, YB3, and YI3. And we also have an extent of reaction. Again, keep in mind these 2 extents of reactions that we have, those are the same extents of reaction, so they're not different variables. So plenty of unknowns. Our equations, not so many. We get the same three material balances, again on A, B, and I. We get two sums of yi have to be equal to 1, and specifically those are on streams 2 and 3. And we have one process spec. So our process spec here is that the single pass conversion is equal to 0.02 or 2%. And so we end up clearly with a lot more unknowns than equations. So we've got 1, 2, 3, 4, 5, 6, 7, 8 unknowns. And our total number of equations is 6. So our degrees of freedom here are +2. So we don't really want to start with the reactor because we can't make a lot of progress right there on the reactor. Moving to our other two units that I drew a moment ago, there's our separator. Separator. Got to spell it right. And if we look at the unknowns on our separator, flashback here to our drawing, the stuff that we're going to deal with the separator are streams 3 going in, stream 4 comes out, and stream 5 comes out. We don't know very much about any of these streams. We don't have any relationships between them, so we have a bunch of unknowns. We don't know anything about how our separator is working. The only thing that we know is that stream 5 has pure A. So we'll just incorporate that directly as part of our unknowns back here. We have stream 3 coming in, stream 4 going out, stream 5 going out. And then we have a set of YA, YB, and YI. We have that set of 3 for both streams 3 and 4. So I'm just using a little bit of shorthand notation there. I mean, you can write that however you want, to indicate that all 3 of those variables are unknown in both streams 3 and 4. We don't have an unknown mole fraction for stream 5 because that's pure A. All we know, or the only unknown about stream 5 is its molar flow rate here, N5, or just its moles, N5. And that's it. There's no reaction inside of a separator. The equations that we get are just the 3 material balances which occur on A, B, and inert. So not good with our separator. We've got 6 mole fractions that are unknown and 3 mole flow rates, or 3 moles that are unknown. So that ends up with 9 unknowns. And the number of equations that we just get those 3 material balances. Don't forget we also get 2 sums of yi, specifically on streams 3 and 4. Remember, we don't get one here on 5 because 5 is pure. And so we've got 5 equations or knowns, and so therefore we have +4 degrees of freedom. So we don't want to look at the separator just yet either, because there's still a lot going on there. And so our last point to look at is our mixer. So the mixer that we're looking at is this point right here. And so the streams of interest in the mixer are streams 5 coming in, 2 going out, and 1 going in. As we mentioned before, we know everything we need to know about stream 1. We know a little bit about stream 5 because it's pure A. And then the last thing that we've not used yet is this process specification. Why didn't we use that on any of the other units? The reason we didn't use it on any of the other units is because it's talking about a relationship between the moles of A in the recycle stream and the moles of A in the fresh feed. So that's talking about some piece of information that connects unit 1 and stream 1 and stream 5. And up until now, if you look at the other degrees of freedom, none of these other units involved both streams 1 and 5. So the overall balance only included 1 and 4, the reactor included only 2 and 3, and the separator included only 3, 4, and 5. We have not had a unit yet that involves streams 1 and 5, which is why we haven't used that process specification yet. So the unknowns that we've got in the mixer, or on the mixing unit, I should say, we don't know how much of the recycle is coming along in stream 5, and we don't know what's coming out of the mixer in stream 2, and we don't know YA2 and YI2. Right, so we end up with 4 unknowns here. How many equations do we get? We get 2 material balances, specifically on A and I. So we did have to use a little bit of logic there to figure out there's not going to be any B in streams 1, 2, or 5. That comes from just carefully looking at the problem. There's no real method to that. It's just looking at what's there. We also get one sum of yi being equal to 1. This is going to occur on stream 2. Remember, we know everything about stream 1 in terms of composition, as well as stream 5. And then we also get one process spec, which is the 10-to-1 recycle that we saw a moment ago. So, ever so conveniently, the degrees of freedom on this system are 0. So we're going to start our analysis with the mixer and learn what we can from the mixer. Once we have the mixer, we can go on to more or less anything that we want at that point, but we'll take a look at what happens after that. So let's take a look at the mixer then. So if we look at our process spec, it's an easy place to start. The process spec implies that the moles of A, sorry, not the moles of A, this is talking about the inert. The moles of inert in stream 5 is equal to 10 times the moles of inert in stream 1. Right, that's what that 10-to-1 ratio means. And therefore, actually give me just a second here. Yeah, that's why that looks funny. That process spec was for A, not I. It wasn't the moles of I, we're talking about the moles of A in stream 5 is equal to 10 times the moles of A in stream 1. Since we're fed 10 moles of A in stream 1, it means the moles of A in stream 5 is 100 moles. So that comes from our process specification. If we look at a material balance on species A, we know that the moles of A in stream 2 is just equal to the sum of those in 5 and 1. So that would be 10 in stream 1 and 100 in stream 5. So we've got 110 moles of A coming in. That's coming into our reactor, that's coming out of our mixer. And then if we do another balance on the inert, all we know about the inert is that the moles of A in, not A, the moles of inert in stream 1 have to be equal to the moles of inert in stream 2, because there is no inert in stream 5, which is going to be equal to 10. Right, so there's our information about our mixer. We now know quite a bit about our reactor. We actually know everything about streams 1, 2, and 5 right now. So if we wanted to try to incorporate that into our other systems, we can go back here and take a look. It doesn't really help our separator very much. If you look at the unknowns in our separator, we didn't solve for any of those unknowns, so we didn't help anything out right there. If we go to our reactor and look at which unknowns we now know, we know everything about stream, everything about stream 2, so we know its total and its mole fractions. So we have essentially eliminated 3 of those, which would push this down to 5 unknowns. We technically don't need one of these sums of yi's anymore, because we would have used one of those on stream 2's, so that would have pushed this down to 5, and so we would have resulted in 0 degrees of freedom in our reactor. So that's a pretty good place to go. Next, we could probably, let's take a look at our overall. No, we don't have any help with our overall because we already knew everything about stream 1, and our only unknowns have to do with stream 4 and the reaction. So no help on the overall. So it looks like the reactor is the next place to go because we can actually solve everything there. So let's take a look at a stoich table. And this is just on the reactor, right? We're not looking at the overall system. We could write a stoich table on the entire system, but we're only going to write it for the reactor. And so we're going to have some species, obviously. We're going to have some stoichiometric coefficients. We're going to have the moles of species in stream 2, because that is our fresh feed. Those moles are going to change by something delta I. And then we're going to have some moles of I coming out in stream 3, Ni3. 3 species to worry about. There is species A, B, and an inert I. Our reaction was pretty simple. It was just A goes to B, so we've got -1, +1. Inerts don't react, so they get a 0. The moles of everything coming in, we just figured out what that was. So the moles of A in stream 2 is 110, B is 0, and the inert is 10. The change, we're consuming a little bit of A, producing a little bit of B, and the moles of I are not changing. So the moles of A in stream 3 is going to be equal to 110 minus squiggle. The moles of B in stream 3 are going to be equal to plus squiggle. And the moles of C in stream 3 are going to be equal to 10. We could add all those up if we needed to. We've seen how that works before. We could get 120 here, no change here. And so we would have a total of 120 coming out. We don't really need to do that right now. But we could do it if we needed to. One additional piece of information that we have about the reactor is that the single pass conversion is equal to 0.02 or 2%. And remember, this is equal to minus the stoichiometric coefficient of A times the extent of reaction divided by the moles of A in the reactor feed. Remember, this is reactor feed because it's a single pass conversion. We're just talking about the reactor itself. And we know a fair amount of this information. The stoichiometric coefficient of A is -1. Squiggle we don't know, but we're about to figure it out. And the moles of A being fed to our reactor is what we just determined a moment ago, which is 110. So from this information, squiggle is going to be equal to 0.02 times 110 divided by +1. Let me pull out my calculator over here because I don't have that number with me at the moment. 0.02 times 110 is 2.2. So with that information, we do have enough now. If we were to go back to this table here, we now know what the extent of reaction squiggle is, so we could figure out what's coming out of every one of these streams if we wanted to. Every component of stream 3 if we wanted to. But remember, the problem statement was asking for, let me flip back here, we were trying to figure out what is F overall. We have enough to figure out what F overall is right now, because if we go back to our definition of F overall looks very similar to F single pass in that it is minus the stoichiometric coefficient of A times the extent of reaction, but now it's divided by the moles of A in the fresh feed, which we happen to know. This was already given to us, so we can look at this as minus the quantity of -1 times the extent of reaction, which is 2.2, divided by the amount of A that was fed, which was 10 moles. And so our result over here is that the overall conversion is 0.22, which is equal to 22%. And so that's as far as this question asked us to go, right? All we needed to do was the overall balance. You could have equivalently gone through this stoichiometric table, figured out what everything is there. If we had done something like that, we then would have had enough information to move on to, I believe, our separator, or potentially our overall balance here. Either one of those, yeah, it looks like the overall balance would have been good because we would then know what our extent of reaction was, and we could solve for the rest of those, and go back and essentially do it the hard way, because the other way to determine F overall is by calculating the moles of A coming in minus the moles of A coming out divided by the moles of A coming in, where we're looking at the entire system. Right, so this would be the equivalent of determining what's the moles of A in stream 1, which we know, minus the moles of A in stream 4, which at the moment we don't know, but we do have enough information that if we walked through the entire process, we could figure it out. But we also know that this value has to be exactly equal to 0.22, because these two definitions of overall conversion will always yield the same result. So we can use either one of those. But maybe it's a little bit faster if we use the one on the top, just because it saves us a little bit of work. Again, there are probably multiple ways to go about this problem. Entirely up to you which one comes to you first, but they all end up having to give the same answer each time. Okay, so that's example 1. Let's look at example 2. Example 2 is a little bit more in-depth. Actually, it's not really more in-depth. It's pretty much the same thing. It's just got a couple extra steps in it. Example 2, we're going to look at a book problem. In your book, this is problem 6.3.18, or 18. So a couple of different ways that you can do this problem. You can either pause the lecture right now and go look at it and see what you can do, or you can obviously pause as we go along and see if you can figure out what I'm going to do before I do it. So at any rate, let's dive right in. I'm not going to repeat the entire problem statement verbatim here because you can go look that up in the book, but I'm going to summarize it with all the relevant pieces of information. One thing that I'm going to do to make this a little bit easier to write is I'm going to summarize all that information, but I'm going to use a little table up here and abbreviate the species so that I don't have to carry around the full names of all these chemical species, because that's going to be just a pain in my neck to write it all down. I'm also going to write the molar masses of all the species, because we're going to need those in a moment. So there's 5 species total. There's Na2S, which we're going to call species A. There's calcium carbonate, I believe that's calcium carbonate, which is, we're going to call species B. A little bit of, again, I think that's sodium carbonate. I don't encounter that one on a regular basis. But at any rate, Na2CO3, we're going to call that species C. And then calcium with sulfur, that one I'm not sure. I don't think that's a sulfate or a sulfite. Again, not something I encounter on a regular basis, so not really sure what that is. And then we've got some water. I'll just call that W. Some simplified molar masses of each one of these. If you look them up, you'll get more digits of precision than what I'm doing here. But we're just going to make these all nice integers so that I don't have to carry around a bunch of decimal points. Again, if you throw more digits on there, they will get more precise. All right. Actually, I guess since the reactor, the whole drawing is pretty big, so I don't think I'm going to try to squeeze anything else onto this page. Let's just move on to the next page and actually draw this thing, because it is a pretty big system. So we have a reactor here, and our reactor goes to quite a complicated little separator. Our separator goes to two more separators. There's an extra separator down here. There's a free stream over there. So I'll just call this, I'm going to actually call all of these separators because there's a few of them and we're not going to look at every one of them. There is another separator here. And then coming into our reactor is one stream here, another stream here. Out of our separator, there's only one stream out of our reactor that goes into our separator, our first separator, and then that first separator does some fairly crazy stuff. Actually, I'm going to move this separator a little bit, stick it over here. We have one stream coming out of the bottom of the first separator going into this guy, one stream coming out of here, and then this stream goes back and rejoins our feed. Then we have almost the same thing coming out of the top of the separator. That goes back over to here and rejoins. Then we have two more streams coming out of our separator. One goes up to our, what is that, third separator? And from that separator comes out one stream over here and one stream up. And then we have one plain old product stream over here out of this separator. So plenty of streams to work with here. Let's take a look at everything that we know. The reaction that's occurring inside here is a pretty straightforward reaction. So I'm just going to write this above our reactor. It's just A plus B goes to C plus D. So that's our reaction that's occurring inside of our reactor. We do know that our single pass conversion, FSP, is equal to 90%, pretty high, 0.9. And we also know, I don't have a good place to write this, so I'm just going to write it pretty down here in the bottom. An additional process spec that we're told is that 50% excess of the CaCO3, which is species B, is fed to the reactor. So if I could add that on my drawing, I would, but I'm out of space on my drawing. And so now let's talk about a little bit of what's showing up in our streams. I'm going to label these, keep going in red, because these are the things that were given to us. This first stream coming in over here is 1,000 pounds per hour. Actually, I'm just going to assume a basis of an hour so that I don't have to keep carrying around that hour term. So let's just say 1,000 pounds. And it consists of 40% A and 60% water. In the fresh feed of the next stream down, it's 1923 pounds. Not sure how they came up with that particular number. And this consists of 30% B and 70% water. This recycle stream coming around contains 30% B. The stream coming out of the separator nearby contains 60 pounds of B. This is also pure, in case that wasn't clear from the process spec or from the problem statement. This, by the way, all this information I'm giving you is the problem statement. There's nothing, I'm not making anything up or doing any analyses up here. The recycle that comes around up here is pure A. we have 100% water coming out this top stream. And then out this first stream up here, we have 80% C and 20% water. Out of the product stream down here on the bottom, 20% species D and 80% water. Okay, so there's everything that we've got. That's all the information that we were given as well. And so we were asked to determine two things in the problem statement. Problem statement asks us first to give us the pounds of species A recycled. So the pounds of species A recycled, here we're talking about this stream. We want to know what's the mass flow rate up there. And then the second part is to determine the pounds of the Na2CO3, which is species C. Oops. Species C. We want to know how much of that is produced. And so the pounds of C being produced is going to ask us to figure out what's happening in this stream. How many pounds of C are coming out over there? And that's all we're given. An important thing to note here is that every percentages, all percent are mass fractions, which is okay, right? There's nothing wrong with being told a mass fraction, but it's going to be a little bit of a pain in the neck because we have to convert as many of these as we can over to mole fractions or use them as some sort of a process specification if we don't want to convert them over into mole fractions. So I'm going to, let's see, what's a good way to do this? I think at the moment I'm just going to leave them the way that they are, and we'll just convert them as we need to. You could take a couple of minutes right now and just go through and convert all of those that we can. So the ones that we could immediately convert are the ones here on the two fresh feeds, and these two here on the streams coming out. We could immediately convert all those to mass or mole fractions if we wanted to, but we're just going to leave them there for now. And see what happens. We can do a series of degrees of freedom analyses, but I'm kind of looking at the way the problem statement is worded right now. It actually looks like we will be able to figure out something about something about problem part B, what's coming out over at the end. We can probably figure that one out pretty quickly because if I look at the overall system, we know an awful lot about it. So the box that I'm envisioning in my mind looks something like this. And if you look at which streams are coming in, we know everything about these two. We know everything about this one coming out. We know a lot about these two coming out. And we know a fair amount about this one coming out. So that looks like a good place to start. Let's do a quick degrees of freedom analysis on the overall system. I'm not going to do a degrees of freedom on every system because there's about, I don't know, 1, 2, sorry, let's look back here. How many of these are there? At the very least, the units that are labeled are 1, 2, 3, 4, because there's a reactor and 3 separators. And then we've got 2 mixing points, so there's 5, 6, and then there's an overall system, which would be 7. I'm not going to do 7 degrees of freedom analyses. Let's just look at the overall system. If we were to draw a box around the entire system, the unknowns that we would have, we're going to have to label our streams here, aren't we? Yep. So I'll go through in, what's a nice matching color? Blue. No, I've already used blue. Green. Let's label some streams here. So we'll have stream 1 coming in, and stream 2 coming in here. So we've got stream 1 here, stream 2 here. 3 and 4 will go into our reactor. We'll have one coming out. We need one over here and one here. We're going to need another one here. I'm just erasing some lines on my drawing here so that I can label these streams. I'm just giving myself a couple of little gaps in here so that they look neat. So 1 and 2 are fresh feed. Then we've got 3 and 4 is reactor feed. 5 is reactor effluent. 6 as our recycle. 7 as another recycle. 8 as this guy coming out. 9 as the other recycle coming back. What are we at? 9 there? Yeah. 10 as one of our products. 11 as another. And then 12 up here. And 13 as water. And so we've got quite a few streams here. You're going to see me flipping back and forth quite a few times here because I'm going to have to reference my drawing. But if we look at the unknowns that we need to figure out for the overall balance, again, keep in mind that the overall is going to be the equivalent of drawing this box here. So the ones coming out of this are, or sorry, going in, excuse me, are 1 and 2. Coming out are 8 on the bottom, 10 and 12 on the right, and 13 on the top. So we're going to need each one of those if it has an unknown. Actually, I can just write my unknowns here and copy them over to the other one. We know everything about stream 8 and stream 1 and stream 2. Streams 10 and 12, we still need to know what their total flow rates are. So we have total mass flow rates of stream 10, stream 12, and we need to know the total mass flow rate of stream 13 as well. We don't need to know any of those mole fractions because they're all already given to us as being either pure or 2 components. However, we do have one extent of reaction. It does not, yes, extent of reaction is usually expressed in terms of moles, but when it comes to writing a degrees of freedom analysis, it doesn't really matter if you choose to put them all on that basis or not, of moles instead of mass. So we can do either one. So let's put our unknowns back over here. There's our unknowns. How many equations do we get? We will get 5 material balances. Which 5 specifically on A, B, C, D, and inert water? So we've got 4 unknowns, we've got 5 equations. We don't need any sums and we don't have any extra process specs. Remember, we're given a single pass conversion, but if we had some conversion that was useful for the overall, we would be talking about the overall conversion. But that is not, keep in mind, the equivalent to single pass. So we don't get that single pass as a degree of, or as a process spec here. So we actually have -1 degrees of freedom, which is over-specified. And so this wouldn't be a bad place to start, just to find out if the problem is appropriately specified, because what this -1 means is that we have more equations, obviously, than we do unknowns, which means we have a way to check whether or not the system is self-consistent. Right, so either that or some of the equations are redundant, and we'll find out when we do the analysis. So let's do that balance on the overall system. In order to do that, I'm going to do a stoichiometric table. So we'll have some species coming in, stoichiometric coefficient, the moles of I. Remember, this is going to be coming in, so if it's coming into the system from multiple places, we'll need to account for that. We're also going to have a delta I, and then the moles of I going out of the system. And again, that might be moles of I going out through multiple streams, so we'll have to account for all of that. Then we'll have species A, B, C, D, and water. In terms of stoichiometric coefficients, we'll have -1 for A and B, and +1 for C and D, and a 0 for water. So a couple of the streams coming in, if we look at C and D, those are both going to be 0. So the streams coming in, if we flip back over to our drawing, are over here on streams 1 and 2. And we can see there that the only things coming in are A, B, and water. There is no C coming in. The one thing that we will have to do is convert those now over into moles coming in, because the Stoich table is always in terms of moles. And we'll just do that one element at a time instead of converting each one. And I'm just going to scribble it over here on the right and then erase it. Since we're watching a video, you can always pull that back out or rewind it and look at it a moment later. I'll just write it in blue so that you don't get confused. The moles of A coming in is equal to that mass fraction in stream 1. We had 40% here times 1,000 pounds for a total stream. And then we have to divide that by the molar mass of A. The molar mass of A, according to my little table that I wrote a moment ago, was 78. So if I throw this into my calculator real quick, 0.4 times 1,000 divided by 78 is about 5.13. Right, so I'm going to take that 5.13 and put it here. Similarly, the moles of B coming in, remember this is to the system, so this would be the equivalent of fresh feed. So here we're looking at stream 2, and stream 2 consists of 30% B, and it's coming in at 1923 pounds per hour, but we took a 1 hour basis, so it's just 1923. And the molar mass of B is 100. If I throw those into my calculator, I've got 0.3 times 1923 divided by 100, about 5.77. So we can put that in here on our table as 5.77. And finally, our water, the moles of water coming in. There's a little bit in both of those streams. So there's 0.6 times 1,000 in stream 1, and there's 0.7 times 1923 in stream 2. All of that divided by the molar mass of water being 18. So that's 600 plus 0.7 times 1923, all of that divided by 18. Total moles of water coming in is 108. We'll throw a digit on there, about 108.12. We'll just carry around 2 digits of precision here for all of these. Right, so that's all we need. As I said a moment ago, I wrote these here just as a quick side calculation. We don't need these anymore once we know how much is coming in to the system. What's our change? Easy enough. We've got each of these. We've got a minus extent, a minus extent, a plus extent, and a plus extent, or squiggle, and a 0 for our inert. And now we have to look at what is coming out of the system. So A is a nice one, right? If I look back at this entire system, there is no A coming out. A is only being fed in through stream 1. If I look at streams 8, 10, 12, and 13, there's no A coming out of there. So the moles of A coming out are 0, and that has to be equal to the moles of A fed, which is 5.13, minus the extent of reaction. And so what this tells us is that the extent of reaction, squiggle, should be 5.13. If we look at the next one, moles of B coming out, flip back over to our drawing here, there are some moles of B coming out. Specifically, those moles of B coming out are down here in stream 8. Right? And we know how much. It's 60 pounds of B. So if I do a quick unit conversion here, 60 pounds of B divided by the molar mass of B, which is 100. I'm getting out 0.6 pound moles of B, and so therefore I know this has to be 0.6, which also has to be equal to the the moles of B coming in, which is 5.77, minus the extent of reaction squiggle. So evidently we have two different ways here to calculate squiggle. I don't need to know anything about A to get a squiggle from B. I don't need to know anything about B to get a squiggle from A. If I calculate a squiggle this way, it should come out to be the same, right? I've got 5.77 minus 0.6, so I've got 5.17 here, which is pretty close. These two values are close enough that we're going to assume that they're the same. We have to pick one. We can't just use them both. But they're very, very similar, which means that when we had a -1 degrees of freedom up here, the part that was essentially overspecified was the fact that A and B are giving us the same piece of information. There's no new information there, but fortunately they are consistent. Had we had different values here, we would have had to stop trying to solve the problem and either rechecked our assumptions or concluded that the problem was specified in such a way that we get contradictions. But fortunately here, we're good to go. The moles of C coming out of the system, so moles of C, and let's see, if we flip back to our drawing, C is only coming out in stream 12. So this location right here, actually let's use blue since we don't have it. That's the only place C is coming out, so that is stream 12. So the moles of C in stream 12 are equal to the moles coming in, which is 0 plus squiggle, and squiggle is 5.13. I'm going to go with 5.13, 5.17 is fine as well, but we do have to pick one. Similarly, the moles of D, let's see, those are coming out only in stream 10, right? We've got a little bit of D coming out here, but there's no D in either 8, 13, or 12. So we're not worried about those, so we have the moles of D in stream 10. Also has to be equal to squiggle, which is 5.13. And finally, the moles of water coming out, which I'm just going to abbreviate as moles of water out, has to be whatever was in, which is 100, what was it, 8? Yeah, 108.12. Where is this all coming out? It's actually coming out in multiple streams. So we have, for instance, we have a little bit coming out here in stream 10, a little bit more coming out here in stream 12, and some more coming out over here in stream 13. We don't actually need that number right now, although we could figure out what it was if we really wanted it. But at any rate, we don't need it per se, so I'm not actually going to complete that particular step. So that's some information that we got from the overall balance. Remember, we're trying to figure out, though, how much is either A, being recycled through the system, and B, how many pounds of Na2CO3, which is species C, that we're making. We have one of those answers right now. So if we look at this particular unit, or sorry, that particular line, that's how much C we're producing in pounds per hour. So, or sorry, pound moles per hour. So if we take that 5.13 and multiply by the molar mass of species C, the molar mass of species C being 106, we get the answer of 543, about 0.8 pounds of C produced per hour. Remember, I wrote pounds for everything, but if you rewind the video, I had just assumed everything was on a 1 hour basis, so I didn't have to carry around that per hour unit, but it is really there. So that's our answer to part B. Oddly enough, we can get that one first. We don't have to solve for anything else. How do we get part A? Part A is, remember, A is asking for what's the amount of, part A is asking for species A in the recycle, so we need to figure out how much is there. couple of different ways that you could do that. The hard way would be solve for everything, which I'm not going to do. The easy way is using our friend the single pass and overall conversions. Remember, we have two definitions of those. The single pass conversion is equal to minus the stoichiometric coefficient of A times the extent of reaction divided by the moles of A in the reactor feed. So the moles of A in the reactor feed is equal to the moles of A in stream 3. And then up on the top is again minus stoichiometric coefficient times squiggle. And we were given a process spec for this, which is 0.9. Why is that convenient? Because we know what this squiggle is. Right, we figured out squiggle from the last problem, or from the last page or slide, which was 5.13. Right, if squiggle is 5.13, we can then figure out what the moles of A in stream 3 are, and then we can backtrack because we know that the moles of A in stream 3 has to be equal to the moles of A in stream 1 plus the moles of A in our recycle stream. Our recycle stream was stream 6, right? So we're doing a little balance on this mixing point right here and saying that 3 basically has to be equal to whatever's in 1 plus whatever's in 6. Right, so this ends up being the moles of A in stream 6. So once we know moles of A in 3, we already know moles of A in 1 because it was given to us. And this is what we were after for problem A, or for part A of this problem. So the moles of A in stream 3, we can get from the expression that we've got right up top, which is 5.13 divided by 0.9. And so we've got 5.7 has to be equal to whatever was being fed. If I flip back to my overall stoich table, we were feeding 5.13 moles of A as fresh feed. And that has to be combined with the moles of A in stream 6, such that the moles of A in stream 6 is equal to 5.7 minus 5.13, which is 0.57. And that is in units of pound moles of A per hour. I believe the question was actually what's the mass of A being recycled? So the mass of A in stream 6 is just 0.57 times the mass of, the molar mass of A, which is 78. So our recycle consists of about 44.5 pounds of A per hour. Notice there are, I can't count the number of different ways that you could go about trying to solve this, right? This is just one of them. Another way that occurs to me now that I'm looking at the problem is if we know, well, we kind of did this already, right? If we know that the overall conversion is 100%, how do we know it's 100%? Because remember a moment ago I looked at that drawing and realized, well, there's no A coming out. What this would tell us is the minus stoichiometric coefficient of A times the extent of reaction over the moles of A fed to the system, which is the moles of A in 1. We can set that, well, no, we can't set it directly equal to that. Anyway, yes, we can rearrange something like this to get the extent of reaction without having to do a stoichiometric table. And then once we know squiggle, we can take that information and return it to the other definition of single pass and figure out what the other extent of reaction is pretty quickly. So there's only a handful of steps here you really need to do. If you could look at it carefully and analyze exactly what we know and what we don't know, you could back out just those two numbers pretty quickly without going through and solving the full problem. But also the way that we've done this right now, we probably have enough to solve everything we need to know. if we wanted to know everything about every stream in the entire system, we now know from that balance that we just did everything about what is happening in streams 1, 3, and 6. Our 50% excess B, which was a spec that we had down here, can end up telling us something about stream 4, because we will then know the amount of B that has to come in, since we will know the amount of A coming in. Then we could backtrack and do a balance on this mixing point right before that in order to figure out just what the mass flow rate is of stream 9, because we know its composition. Once we knew everything about 3 and 4, we could do a Stoic table on our reactor itself. And probably, yeah, we could figure out everything there to get us 5. And then everything would sort of fall apart after that. We know everything going into 5, everything coming out. Yeah, we could probably figure out what's happening after that just by writing out the material balances for everything that's coming out. Because we can do balances over these streams here. We know basically the mass or the mole flow rates of all of these streams coming out, which are 8, 10, 12, and 13. And so therefore the only things we don't know about our separator are things like stream 7 here and stream 11. But we can get 11 by doing a balance on this separator. We already know 10. We can get everything about 7 by doing a balance across this separator, because we know what's coming out. And then we can use all the equations on the separator in the middle, this guy, to check our answers, because we would already know everything about all the other streams. But we don't have to actually solve for any of that. We could just sit here and do that if we wanted to, but the problem doesn't ask us for any of that. So it's not necessary to keep going after that, unless you want to. If you want to try and figure it out, you can probably do it with everything that we've got here. You will encounter slight variations, right? Remember, we came up with 2 slightly different values for the extent of reaction. Those 2 should be exactly the same. They're very close here. They're within, 1% or something like that. But depending on which one you use and where you do your checks, you will find small variations. I would not expect anything to vary by more than about 2% if you do a check like that. Probably 1% is about as much as we would expect. Right, so you're going to practice a couple of those on your homeworks. One of them is a little bit bigger than the other one. But that's the general approach. As we saw with the simple one, if there's only a handful of units, you can often do the degrees of freedom analysis pretty quickly and figure out where to get started, and the dominoes sort of fall after that. On a bigger problem like this one, sometimes you want to use a little bit of logic first before you try to write degrees of freedom analyses on all of those systems, because you may not need information on all of those systems. But you can always do that. It will work. It'll just take a little while. And that's the last of our material on multi-unit processes. We are going to keep coming back to this stuff over and over and over again, especially when we get to energy balances. You can't get away from the material balances. We just won't explicitly spend this amount of time on them when we're doing the energy balances. What we're going to talk about in tomorrow's lecture, Tuesday, is a brief recap of how gases behave, so that later in the week we can talk about a new topic called vapor-liquid equilibrium. All right, so I look forward to seeing you all tomorrow. I hope you got a chance to see the eclipse. It was pretty nice, even though we're in San Diego and we only got a 60-some%. It was a really nice eclipse. It's not coming back. I think we get another one here in 2024, but it's over on the East Coast, so we probably won't see much of that one. All right, thank you all very much. I will see you tomorrow.